Now let's look at this other example here. So this is example number 27.10. Now this example is discharge. So we're discharging. So if you look at the question again, it says that suppose that we have a capacitor that has a capacitance of C, and this is being discharged through a resistor that has a value of R, as shown in this figure right here. So again, remember that when you discharge, you want to place a switch right there so that the capacitor can power this resistor. It says that after how many time constants is the charge in the capacitor 1/4 of its initial value? Now, if you remember, we said that whenever you when you discharge a capacitor, Q as a function of time is equals to QI times E to the negative T R times C. So you want this charge to be equals to 1/4 of this maximum value. So you want this to be QI over 4. So if you have QI over 4 is equals to that, you rearrange this equation, you get this. Then if you remember from your algebra, if you want to solve this equation, you take the natural log ln. So that's the natural log. You take natural log. Now, when you take the natural log, you can say that this is equals to that, and solving this equation, you get the time as equals to that. So it's about 1.39 times the time constant, where the time constant is given by R times C here. I hope you guys see how we got from here to here. Because so ln, so natural log of 1/4 is the same as negative the natural log of 4. Does that make sense? You guys see why that is the case?
You gotta do the subtraction, right?
You gotta do the subtraction, right?
ln of 1 minus ln of 4.
Yeah. And ln of 1,
0.
0. Okay. Now the energy stored in a capacitor decreases with time as the capacitor discharges. Now, after how many time constants is the energy stored in a capacitor equals to 1/4 of its initial value? Again, if you guys remember this equation here, how to calculate the energy on a capacitor. Now, if you just substitute your Q of T, so remember that your Q of T is equals to QI e to the negative T. If you take all of this and you substitute here and you square, you get all of that. And then you want so this would be the maximum charge. So you want the charge to reduce to 1/4 of that maximum value. And so you solve that equation, you get the time is about 0.693 times the time constant. Now, if you remember, we said that there is a current that is flowing here, I, as a function of time. And this current is given by I of t. So I as a function of time is equals to epsilon over R times E to the negative T over R times C. Now, if you know what this current is, you can also calculate, for example, what is the power, so P. So what is the power given to the resistor at any time? It's just given by I squared times R. So power is a function of time.
Where did they get the 2t? So in the equation says e to the negative 2t over RC.
Yeah.
Where's that 2 coming
The
from?
2 comes from, it comes from taking the square of this quantity here.
Oh, okay.
Because if you take the, I apologize for this being a little bit too messy here, but so you're taking Qi, so Qi e to the negative t over RC, and then you want to square all of these. So this square is going to apply to Qi, and then it's going to apply to 2. So it's 2 forms, it's Qi squared times e to the negative t over RC, all of that square. So that 2 goes into that exponent there. Is there any other questions about this section here? Now, what I was saying is that when this capacitor is connected like this, so this is going to act as a battery. So it supplies a current, and this current is going to go through this resistor. Now, the current as a function of time is given by this equation. Now, I can calculate the power as a function of time by taking the current, so I squared times R, right? Then, for example, if I want to calculate the total energy, so the total energy given to that, to this resistor, I can take the power as a function of time, and I multiply it by dt, and then I can integrate all of this from, let's say, from 0 to infinity. And if you do that, you should get exactly this quantity here. You should just get, it should be the same as Qmax squared divided by 2c. Now, what is Qmax squared? So again, remember this Qmax. What is this quantity here, Qmax squared? You see that as the maximum energy stored on the capacitor? So what I'm saying is that if you let this capacitor power this battery, after a very long period of time, all of that energy is given to the resistor. And that makes sense because it's just conservation of energy, right? If you have 100 joules of energy on the capacitor, and this is connected to a resistor, then it's going to be losing that energy until all the energy goes to the resistor, then there is no energy on the capacitor. Okay. So if you guys try this, I want you can try this at home to see if it's going to give you that equation. It's a good practice. So again, calculate your power is just I squared times R, and then integrate that from 0 to infinity and confirm that it gives you Qmax squared over 2c. Okay, let's see. Now let's look at this. It says, what if you want to describe a circuit in terms of the time interval required for the charge to fall to 1/2 of its original value? How is the half-life? Okay, so the half-life, so again, this is just something that is additional here, but so the half-life is just the time that is going to take for the charge to drop by half. So at t equals to t half, the charge on the capacitor has reduced by 50%, And so if you solve that equation, this tells you how the half-life is related to the time constant. Again, I don't think you guys need to worry about this half-life that much, but just think about it as the time that it takes for the time that it takes for the charge to reduce by 50%. And I think it's just like very simple mathematics, right? Right, so this is what I was talking about here. Again, exactly what I was talking about here. So if you take this current at any time, which because Qi is equals to C times epsilon, so it means that this is equals to epsilon over R into the negative T. Now take this and multiply by dt and integrate this from 0 to infinity. If you do that calculation very well, you end up with this equation here. So again, notice that all of this is the same as Q max. Which makes sense. So we're saying that the resistor is going to get 100% of the energy from the capacitor after a very long period of time. Okay. Now I'll show one example here. So this is an example of, I just want to talk about this final example here. So now suppose that you have a system that looks like this. And let's try to make sure that we understand exactly how this system works here. So you have so generally, so this is called the ground. So the ground is just a reference voltage here that is taken as 0 volt. And then if you maintain this to be 120 volts, such that the voltage between this point and this point is equals to 120. And then what I'm going to do is that I'm going to connect 3 devices here. So 3 devices that have resistances R1, R2, and R3. Now, what you want to remember here is that those 3 resistors are connected in parallel. So all of those 3 resistors are going to be receiving the same voltage, the 120 volt, right? But what we're going to do is I want to calculate how much amount of current goes through each of these resistors. So we're going to assume that, for example, suppose we have a microwave that is rated at 1300 watts, and we have a toaster that is rated at 120 watt, and a coffee maker that is rated at, so those are called powers, right? Then it means that I can calculate the current. So again, let me write this equation. I think we've seen this equation before. I gave you this equation. I said you can calculate power as voltage times current. But you can also calculate power as I squared times R. So each of those equations will give you the power. So in this case, since we know current and voltage, this is the equation that we can use. But the point is that you can calculate, notice that the voltage is the same all across. So it's 120 here, it's 120 here, it's 120 here. So in this circuit, the toaster is going to draw 8.33 amps of current. The microwave is going to draw 10.8 amps of current. And the coffee maker is going to draw 6.67 amps of current. Now, if I were to sum all the current, so this current plus this current plus this current, it gives me the total current. Now, do you see that because this point is a junction here, so whatever current comes here is going to split into 3 parts. So it means that if you add these 3 current up, it tells you the original current that goes through the circuit breaker, right? And so in a real household application, you can put a switch here. You can put a circuit breaker. So this is going to help because this will check what the current is. So if the total current is greater than some threshold value, so there is some threshold value. Which, let's say, for example, this could be like 30 amps. So you want to check that this total current is always less than that value right there.